All right, so now we're looking at grasshopper eggs. So the percentage of southern Australian grasshopper eggs that hatch as a function of temperature for temperatures between 7 degrees and 25 degrees C can be modeled with our function g of t equals negative 0.0065 t to the fourth plus 0.49 t cubed minus 13 t squared plus 136.3 t minus 394%. Okay, so this is going to give us a percent out, and then it's going to be for whatever temperature, okay? So what do we need to do? Well, we know that we're going to have to find the derivative of that. And so that's going to give us a negative. And we plug in 4 times that. That's going to be 20, 24, 26. So that's going to be 0 to 6t to the third. Then it's going to be plus, and 3 is 18, 12, 13. 27, sorry, 12 to 1.47 t squared, and then minus 26t plus 136.3, okay? So I think that should get us everything we need after we've taken the derivative. And so now what we need to do is we need to find where those points are. And so what I'm going to suggest is, again, using our calculator, so let's get rid of that. Now, we know what the derivative is, so we can type it as well as the actual function. So let's type both of those in here and see if it makes a difference which one we use, because sometimes it will, apparently we found, and sometimes it doesn't. Always remember to go back down when you're having something over an x squared, because x squared goes automatically down, but the others don't. Oops, wrong button. Plus 336.3x minus. All right, so that's our actual g function, and our g prime we said was negative 0.026 x to the third, arrow down, plus 1.47 x squared, and minus 26x plus 136.3. All right, so now we have everything. Our graph windows are probably going to be all messed up. And this one was from 7 degrees, I believe, to 25. And so we can go by, I don't know, 3. I don't care what it matters. Now our min, let's see here. Well, it's going to be a minimum of 0% and a max of 100%, hopefully is how it's going to work. We can go by 20s. All right, so our derivative is going to go below the graph, so we'll have to actually go below here on that min. So let's go negative 50. I don't know if that's going to be far enough, but we'll see. Yeah, there we go. All right, so that's original, that's our derivative graph. And so what we need to do then is we're going to numerically solve again, okay? And we're going to 0. And this time, actually, you know what we need to do? Well, this time, let's clear that out, and let's put just in our derivative that we took, okay? So 1, 2, and then we can say, okay, we're going to take and find that derivative and find where it's at. Well, let's try close to 1 n, 7. Oops. So we get the 9.4371. Okay, so that's going to be 1. What was the other end? 25. Let's try that one. And it's saying that there's only 1 point in there for that interval. Okay, and so that's going to be a key. So what we have then is our t is going to be then 9.4371. And now we probably should start putting temperature, degrees, everything else. So what temperature between those corresponds to the greatest percentage of eggs hatching? All right, so that was this, degrees C. And what is the percentage of that input? Well, now we need to find what G of 9.4371 is, okay? So now we go back over here and we find this. We go to our graph and we do a calc value, And if we put in 9.4371, we get 94.7811. So that's going to be 94.7811, and that's percent, and that's that degree. So at that degree, we get that much percent hatch from our eggs, okay? Now, what temperatures between correspond to the greatest period? What is the percentage input? What temperatures between percent? All right, so now we have to figure out what's the least between there and there. Well, we didn't find any other points. So actually, we probably shouldn't say that's the max until we find what G of 7 and G of 25 are, because we need those 2 points as well. So we can't really say that's the max, but that's the max at this point in time. So now let's do a 7, 75.5635, and then the other one was 25, and 5.6875. Okay, so now let's write those down. So we had for 7, it said 75.5635%, and this one was 5.6875%. All right, so now we have all of the numbers we can get. We had this one, which is the only one that came up between, the 7 and the 25. That was the only other point that was in there that had an extreme point. And so looking at this is going to be our absolute max. And then this one is going to be our absolute min, okay? So the 25 degrees C gives 5 point, if we just round it to one decimal place, it doesn't really matter, I guess, on that. We'll say 5.7% hatch. And at 9.4 degrees C gives 94.8% hatch. Okay. And again, those are going to be our extremes, the absolute extremes, absolute max and min, here, max and then min. All right, what about river flow rates? All right, so we suppose the flow rate in cubic feet per second of a river in the first 11 hours after the beginning of a severe thunderstorm could be modeled as such: def of H, where H is the number of hours after the storm began. What are the flow rates for H equals 0 and H equals 11? Well, H of 0 equals, well, that's just going to be 123.02 cubic feet per second. H of 11, that's going to be at the other end, because we're having endpoints, because that's what we're looking at. We're looking at our endpoints right now. Well, now if we plug in this, well, why don't we do this? Let's plug it in to our calculator. Let's clear all that out. And so that equation was a negative 0.865 x cubed, oops, arrow down, plus 12.05 x squared minus 8.95x plus 123.02. Okay. All right. So now what we're going to do is we're going to go math. We're going to up here, numerical. Now we're going to do what we started that one other time. We're going to take the derivative. So we're going to do math 8. We want the x. Now we want y1. And then we went over here. We want that to be x. We want to calculate that. And so if we plug that in, let's plug in a 0 and kind of see what it is. Have to actually hit this button up here. We get 0.3875. So that's going to be hopefully the leftmost point. Now, if we plug in the other end, which was 11, we can see what that gives us. That gives us 8.8995. All right, so those are 2 points. And so I've written that down. So now let's go to our graph. Okay, second graph. Here we go. And now we need to set our windows correctly. So we're going to go from 0 to 11. We'll go by 1. And here it's going to be probably pretty big. Maybe we'll go from 0 and we'll go up to, I don't know, 400. We'll go by 50. All right, so that's what our graph looks like. So, we have this low, then it reaches this pinnacle when we have the most stream flow, and then it starts decreasing. And so what we're going to do is we're going to do our calculations. And so we needed to have f of 0, which we knew. Now we have to do f of 11. So we get 331.305. Okay. Then we had to do that 0.3875. Oops. Oops. 5. So that gives us 121.31093. And again, probably 0.31 is as good as we need. And then our last one was 8.8995, and that's 388.047. So that's going to be our absolute max, obviously. And so let's go back over here. So we had h of 11, we said. We calculated that as 331.305 CFS. And then over here, we did our derivative. And our derivative is f prime of h equals, now if we take and multiply that, that's going to be a negative 2.595 h squared plus 24.1 h, and then minus our 8.95. And we plug that into our calculator, and we got x, or h rather. H was equal to 0.3875, and H was equal to 8.8995. So then we went over here and said, oh, these are F's, not H's. Too many H's and F's. We should just use F and X always. So that's F, then we have F of 0.3875, and we said that one was 121.311 CFS, and F of 8.8995 was equal to 388.047 CFS, okay? So where is the minimum? Well, at 123, 120. So this one is going to be our absolute minimum. And the max 133,388 is going to be this one, and that's going to be our absolute max. Okay. So that's what part B was. It was asking for what are the absolute value or absolute max and min. And so that was B. And then what were the flow rates there? Well, that was really just that part there. Okay. But we had to do this to be able to get to there, and we could plug this into our calculator and then plug in and do our solve that way, or we can tell find the derivative yourself and then do it, and we plug in values, and we did it that way. So we did our derivative, so we found that, and then we could plug that in and do that. Okay, what else do we have? All right, well, let's pause there and I'll come back for more.